Okay, so we are still on 1G, and we talked about polynomials, and the key concept, I guess, property when it comes to polynomials and long-term behavior is that the polynomials behave like their leading term. Now we're going to look at, oopsie, a lot of delay here in my writing. Whew. Rational functions. Oops, don't put a line through it. Under it. There we go. The laptop's not as good as my PC, so it's a little laggy, but that's okay. So, we first want to understand what is a rational function. A rational function is simply a fraction of polynomials. So I'll have polynomial over polynomial. So let's make some examples. An example could be 2x, that's a polynomial, over x squared plus 1, that's a polynomial. So it's a fraction of polynomials. That's a rational function. Of course, I could have 2x cubed minus 7 over 1. Constant, the number is still a polynomial. It's just the constant term. So this is, of course, equivalent to the polynomial, which says that polynomials are a special subclass of these rational functions. The rational functions extend the family of polynomials, and we have more fundamentally different kinds of functions now as well. So if we want to break it down to a representative basic function, it's going to have an interesting denominator. So the basic function that we want to add is y equals 1 over x. As simple as possible, a numerator. The variable has to be in the denominator to really capture this new kind of function. Now, many of you have seen this before, familiar with it, so I won't dwell on this for too long. Let's get a graph of this basic function. Whether you make a table, whether you remember, regardless, I have much more interesting properties here. When I plug in 0 for x, there is no y value that I can calculate. The function is undefined. And as I plug in x values closer and closer to 0, let's say from the positive, my y values blow up. So my graph is going to look like this, less wobbly, but still the same, where as I get close to the x value of 0, my y values just increase. And the closer I get, the bigger this y value is going to become. Plug in x values, convince yourself, not hard to do. As I take bigger and bigger x values, then we have seen yesterday what happens to 1 over x. It's going to get closer and closer to 0. So the y value gets closer to 0 as x gets bigger. Now, similar things happen on the negative side. I just happen to have everything negative. So I'm approaching 0 from the lower negative side, and my y values blow up in size, but obviously negative. So I have nice symmetry, a mirror image of these two pieces. So first of all, let's clarify the long-term behavior. As x approaches infinity, that's my language, my words for saying I'm looking at bigger and bigger x values with no end in sight. Then 1 over x or y, is going to go to 0. And that's also the case when x approaches negative infinity. I'm just going to the left. Yes, the y values will always be negative, but in terms of what happens to the size of the number, it's still going to be 0. All right. So when we have a number here that the function approaches as x gets really big positive or really big negative, then we're going to call that a horizontal asymptote. Please make sure that your mic is muted if you are not asking a question, since the background noise distracts people. We are 3 weeks in now. It shouldn't happen anymore, right? Horizontal asymptote is this y value, and it's the line, in this case y equals 0. It's a horizontal line, horizontal straight line. In this case, it just happens to sit right on the x-axis. It's what the graph is wanting to do long term, far to the right. It's flattening out, and it wants to be this horizontal line that sits at y equal to 0. Far to the left, the graph, though it's never going to get there perfectly, it wants to. It's getting closer and closer to being flat, horizontal at 0. But there's always a small little gap, right? It's just the behavior. It's behaving like that. And the further I go, the closer that behavior is. Now, I also have other kind of quote-unquote long-term behavior, that as I get close to 0, the y value blows up. Now, for now, I'm just going to write this in words, and we have to refine the mathematical language a little bit later. So I'll say if x approaches 0 from the right, then my y value approaches infinity. I'm not going to use an arrow for what happens to x right now, since we don't need to make things unnecessarily complicated with a lot of things to remember right now. The point is, I have another long-term behavior, but it's flipped around. Y is blowing up as x approaches a number. And I'll squeeze it in here because something different happens as x approaches 0 again. The x value where the function is undefined, but from the left. So I kind of have to write a sentence to just distinguish between these two, right? The behavior of y is different. However, it's an infinity. Let's say it here. Some infinity. I don't care if it's positive or negative. It's one of the infinities. When that happens, the graph wants to become a vertical straight line. The line that sits right on the y-axis in this case. The closer I get to 0, the more the graph behaves like that line. So we're going to call that line a vertical asymptote. It's the vertical line sitting at x equal to 0, and the vertical line has an equation x equal to 0. Now we'll see soon that it doesn't have to sit on the y-axis. Horizontal asymptote doesn't have to sit on the x-axis, but we call those asymptotes regardless. So there are more interesting properties that my basic rational function has, and it's mainly in this long-term behavior situation. I have a point here. If I want to keep track of something because of a stretch, the point 1, 1 could work, for example. I have here when x is -1, then of course y is -1, and so on. But the interesting things are these long-term behavior properties of the function. So this is going to be another basic function that I can add to my library of functions. So far, really just the basic polynomials. We're going to add a little bit systematically, and this is one of them, just like the square root was one of them, and my library of basic functions are growing slowly. It's all good. All right. So now I want to just look at a little problem where we can do some transformations, and I want to look at problem in 111, number, let's go with 3. It's a nice one. Where are my problems here? There's the problem book. Hello. Number 3. So I have y equals 4 over x plus 2. Okay. So I'm given here 4 over x plus 2. Now I'll pick a simple one. You can, of course, practice the others, but we'll do this full one at least. So, of course, I'm going to start with y equals 1 over x. That's what this is built on. I think I can squeeze it in. Then I'm going to go to 4 times that, and I can put the 4 at the top, but it is really 4 times the right-hand side, right? And then we will lastly replace the x that I had previously with an x plus 2. Okay, so I want to map out my function transformations first. Now I have a plan, and now I'll graph it. So I want to set up my 3 graphs here. They're going to be a little small, but that's okay. I think we can squeeze them in. I hope. This last line is not working for me. I have to go slowly. I think my laptop doesn't like it when I go fast. The laptop is doing a lot of things. It's recording the video, it's streaming the video, multiple places, lots of things are happening for poor little Mr. Laptop. This is problem 111, number 3. 111, number 3. So, the basic graph, I should know now. It's in my library. Try and make it smooth. Oof, my laptop is very laggy right now. Keep it smooth. It's very hard when you can't see your hand and there's lag. I'm full of excuses today. Okay, now our transformation is multiplying the right-hand side by 4. So that just stretches everything out. Now, my graph is really small. I'm not going to even attempt to think how this is going to get stretched. But I keep track of a reference point to indicate that, oh, if my shape isn't looking as if it's stretched, I indicate that, yes, it has been stretched vertically, whether you can see it or not. And that's the benefit of the reference points, that you don't have to alter your shape and deform it to the point where it's not comfortable anymore. So that's good. We've stretched it. There's evidence. Now I replace x with x plus 2, which means I shift everything from to the left by 2 units. And now the vertical asymptote that sat at the y-axis becomes visible. We'll put it over here and now sits at negative. That's an ugly -2. Put it over there. -2. My Shape is still the same. I try and ignore the y-axis when I draw the shape because this is now, for reference purposes, my center line is this vertical asymptote. Now I'm running out of space here a little bit. Whoa, that was bad. Just make it as bendy as possible. I'm going to blame my software today. So my bottom reference point is now sitting at -3, and of course still -4 for the y value of that point. Everything just shifted to the left. My other reference point is sitting at, I only moved 2, right? So it's sitting at -1 and 4. A little bit messy, but there it is. Now I can, of course, find a y-intercept. Do they actually even care in the question? I don't know if they actually care. State the sequence of basic transformations and graph it. All right. It's always nice, though, to have a y-intercept. Basic requirement here is a y-intercept. Well, that looks like a graph. Let's do it separately. Y-intercept, because it's not hard to do, right? I set x equal to 0. What do I get? I get 2. 4/2. So that's a 2. I at least want to show that. X-intercepts, if they don't ask, don't even bother. Because sometimes x-intercepts are really hard. Think of the quadratic formula. When the parabola is so easy, quadratic formula is much more work than everything else is. So whether they ask for it or not, I want to do the y-intercept. It's nice. It's a nice gesture. All right. So hopefully that graph is fairly familiar. How do you feel so far, technical issues aside? We won't graph it, but we want to see something a little more complicated just so that we're ready. So I'll make a new page here. Just to save time, I'm not going to graph that example because once we have the sequence of transformations, it's really a formality, I hope. And I want to do problem 111, number 8. And I'm not going to bother showing it. I'll just show you here. It's 3x minus 7 over x minus 2. All right. Now here is the pickle with this. There are x's in the top. Well, there's an x in the numerator. So you might be tempted to think, oh, I see an x minus 2, so that means I shifted to the left, to the right by 2. Yeah, but that's only when the numerator is already handled by a simple stretch transformation. This one is a rational function, but the transformations are not clearly visible. Think of the quadratic function that had a general form, and I couldn't see the transformations. I had to isolate them first in order to see them and the sequence. Now the method there was completing the square. That's not happening here, but I have to still rewrite this to figure out what the transformations are. So I'll say here, I can't see each transformation that is happening. So how do I rewrite this? How to rewrite this so that I can see it? The answer is with long division. I know, another favorite, right? It was completing the square. Okay, block that out. Long division, yeah. Long division of polynomials. So let's see how that works. Now, I know whether you remember it or not, you've done all these things. And you've done all these things in a much more complicated way than we're going to need here. So I'll draw the parallel between long division of uh, numbers versus long division with polynomials. Now, it's not going to be so bad because our polynomials are going to be quite small for our purposes. Let's remember, let's compare this to, let's say, 7 over 3. I want to rewrite that to, of course, what I know, the whole number portion and then the fraction portion. Right now it's an improper fraction. How do I do that in elementary school? See, I'm not asking much. I'm asking elementary school stuff. Well, this is equivalent to 7 divided by 3. So that means 7 is inside the house, 3 is outside the house. I'm dividing 3 into 7. Then I go. 3 goes into 7. How many times? 2 times. 2 times 3 is 6. That's how much I've used. I take that away. I have 1. And that is what we call the remainder. This 7 over 3 can then be rewritten using the quotient, the divisor, the remainder as 2, I'll write it as a plus, 1/3, or 2 1/3. The plus is just hidden in the mixed number. Okay, everyone should remember this. It's elementary school, grade 4, let's say. We're going to do the same thing. We have, however, little polynomials. Our numerator is inside the house, 3x minus 7. Our divisor is x minus 2 outside the house. But we're doing almost the same thing. Almost the same. We have multiple terms, so there's a slight adjustment. So what I'm going to do is first compare leading terms when I ask the next question. 3 goes into 7 how many times? X goes into 3x how many times? Get rid of my circles there. X goes into 3x 3 times. Then I multiply 3 with the whole divisor, just like I multiplied 2 by 3 in the elementary school example. Okay, so 3 times x is 3x. 3 times negative 2, negative 6. This is sort of what I've used so far, and I need to take it away, all of it. Now, by design, the x terms will cancel. 3x minus 3x. Negative 7 plus 6 is negative 1. I can't fit x anymore in. The degree of this negative 1 is lower than the degree 1 with the x. That's my remainder. So now in the same way, I have a quotient, divisor, remainder. I put them together in the same way, which is the quotient plus the remainder over the divisor. I can't say it's exactly the same, but it's extremely similar to elementary school concept. So this is now going to allow me to see the transformations. I have a negative there. I replace x with x minus 2. Then I add 3. So let's do it. And again, I know for a fact, because I've taught pre-calculus, that you have done long division. I can't help if you blocked it out. But we're not going to do high degree polynomials, so it's actually simpler than that. So now our transformations, that'll only make the sequence. I'm not going to graph it because that should be a formality, I believe. 1 over x. I'll do 2 lines. It's not an approaching behavior arrow. Then I will go to multiplying the right-hand side by -1. I'll put the negative at the top because it looks nicer there. Then I will replace x with x minus 2. And lastly, I will take that right-hand side, squeeze it in the space I have left, and add 3. So what are the graph transformations? Let's just talk through them. I have a reflection. It's vertical, right? Vertical reflection. Let's write that down here. Vertical reflection. Then I have a replacement of x with x minus 2. So that is a horizontal shift by 2 units to the right because it's x minus 2. And lastly, I'm adding 3 to the right-hand side, making it a vertical. Waiting for my S to show up. There it is. Woo, buddy. Lag. A lot of lag. I just want to undo my H. There we go. You're almost there. You're almost there, laptop. You can do it. Vertical shift. And then you can graph it if you want to. Okay. So in order to see the transformations, if there are x's in the numerator, I have to do long division. If there's only a number in the numerator, well then no problem. The transformations are easier to see. So there's a little bit more of a variety in these. It's a different kind of function. I might have to handle it differently. But the key transformations are still there. It's just a matter of seeing them. All right. Any questions or thoughts as you try and remember long division? Or does everyone remember polynomial long division? I don't know. Maybe you do. Sounds good. So that was the worst part over. Long division, that's the worst part of this rational function transformation thing. Let me just make a new page for the next little bit, but the next little bit is not too bad. I just want to go back to my long-term behavior issue. Now there's a lot of similarities here with what we did with polynomials. When we looked at transformations, we kept the functions simpler, that you can't conveniently make transformations from any polynomial. Sometimes it's just the generalization of completing the square is just a mess no one wants to do. Same thing here. When we look at transformations, we contain them and make the rational functions fairly simple, not high powers of x or anything like that. But for polynomials, we could ask the general question of long-term behavior. So let's just remember, it was yesterday, but still remember. As x approaches plus or minus infinity, a polynomial behaves like its leading term. That leading term eventually dominates the whole thing if I just go far enough to either side. That's the key property of polynomials. So now I want to ask the same thing about rational functions. When I go far to the left or right, a rational function rational function behaves how? That's the question. Now, it's really all good news, because a rational function is just made up of a couple of polynomials. The news is pretty good because it's polynomial over polynomial. So let's just do a couple of problems and then we see it's actually quite straightforward. But there are more things that could happen as an answer, but it's not complicated to look at because I'm building on my knowledge of polynomials. So, I mean, yes, we have to build the layers correctly, and this is the theme of the course, that when we talk about a topic, make sure that you understand that topic, because the next one might and probably will build on that. And if you're, for example, shaky about polynomials, then rational functions are much more difficult than they need to be. But if you have polynomials down, building the rational function concept on top is not that bad, for the most part. So I want to do problem 112, number, I'm going to go 13. Apparently I want to do 16 first. All right, apparently 16 is first. Don't know why. I'm just going to write my function here. Y is equal to, instead of showing it, I have it in front of me. You can just take my word for it, or you can double check. And the bottom polynomial is x squared minus 9. Question is, here's my question. If x approaches negative infinity, then y approaches what? Same question as we did yesterday. Same problem set. It's just now it's a different kind of function, and potentially then the way I handle that is different. This time it's a rational function, but they're made up of polynomials. So I can answer this question if I just look at how the numerator behaves, how the denominator behaves separately, and then maybe that'll give me some insight. So I want to look at the behavior of each polynomial. The numerator, 3x squared minus 5x minus 2, behaves like its leading term because x is going to one of the infinities. Its leading term is 3x squared. That's the first one. Second one, the denominator, x squared minus 9, behaves like its leading term, x squared. And I can only say that, let me just emphasize, I can only say that when I'm looking at the two extremes, x going to positive or negative infinity. Anything x approaching a specific number, that's a whole different question for a whole different chapter that we have to do later. This is only long-term behavior. So now that means, so if x approaches negative infinity, then I'm going to write it in words, though the arrow is exactly the same. Y behaves like, I'm going to put it over here, just so I have space. 3x squared over x squared. again, let me make this extremely clear. I will never say y equals 3x squared over x squared, because it doesn't. It simply wants to become that function. It is heading closer to that function as x gets bigger and bigger in size. It's whatever that function does, y wants to be that. It's heading closer and closer towards it, but it's never going to be the same, which is why I'm emphasizing behaves like, not equal. Never equal, actually. Now I can simplify this. Let's do it over here. 3x squared over x squared simplifies, whoops, that was an I. I should really not try to undo. My laptop does not like that. Simplifies to, well, I have 2x's at the top, 2x's at the bottom, so 3. So, my conclusion, if x approaches negative infinity, then y approaches 3. Now, I have no idea what this graph looks like, right? This function has some fancier polynomials. It's not even super fancy. It's a couple of quadratic polynomials, and I still don't know, without a lot of effort, what this graph looks like. But that's not the question. The question is simply, if I go far enough to the left, because negative infinity for x, what is happening to the function? What is happening to the graph? What is happening to the y values? They are approaching the horizontal line that is sitting at 3. I don't know how. It could be from above. It could be from below. I don't know. And that's also not something I should be worried about right now. Regardless, it wants to become a horizontal line as much as possible. And I do that by just going further and further to the left. So that then means, because I am approaching a specific number, I have a horizontal asymptote, which is y equal to 3. It's the equation of this horizontal line. All right. So the long-term behavior question for this drastically different kind of function, many more interesting things can happen with rational functions than they can with polynomials. The long-term behavior question can be answered because the function is made up of a couple of polynomials, and each one of those polynomials behaves like its leading term. So now I just have the long-term behavior be the same as the ratio of the leading terms, because they're polynomials. Let's do another one. And I want to do problem 112, number 13, where I just have exactly the same question. I just have my function y, 4x over x squared plus 4. Same question. If x approaches, in this case, infinity, then what is happening to y? So hopefully you feel that this question, because I understand polynomials, is really not difficult at all. I simply look at the ratio of leading terms. I can write it even shorter. If x approaches infinity, that was an ugly infinity, I apologize. Let's make it nice and balanced. Then y behaves like the ratio of leading terms. This is an arrow. This is not an equal sign because it's behavior. My mathematical translation for behaves like is that arrow. Okay. If you say equal in a test, I'm going to have to subtract some marks because it's not the same thing. And it shows you don't understand that we're looking at behavior here. Now this can simplify to, let's simplify it. Simplify, sorry, that was an arrow too, right? Let's make a different arrow, double arrow. Double arrow doesn't have meaning for us right now here. Simplify to 4 over x. I have one x at the top, two x's at the bottom, so I'm going to be left with an x at the bottom, unfortunately. Okay. However, that's not a big deal. I simply have to look at the behavior of 4 over x. Well, if x approaches infinity, then what happens to 4 over x? We've discussed this yesterday. It's going to go to 0. And so y is going to approach 0. Y behaves like the ratio of leading terms that I can simplify to make it easier for myself. So what this is saying is, if I look at, let me zoom in. If I look at the original function, 4x in the numerator, x squared plus 4 in the denominator, the whole thing shrinks down to 0 eventually. In the middle, no, other things are happening. I have no idea. Long term, the whole y value shrinks down to 0, which when you think about it makes sense because x is growing, 4x is growing, and x squared plus 4 is growing. But the parabola, x squared plus 4, is going to grow much faster eventually. And it's going to completely outgrow 4x, dominating that fraction. And because it's sitting in the denominator, it's going to control the size and make it small because the denominator is going to eventually be much bigger than the numerator. I am looking at this as a rational function, which then tells me long term it's behaving like the ratio of the leading terms, which I then have in a circle here. I then see, well, can I simplify this a little bit to make it easier for myself? Yes, it simplifies to 4 over x. Now I ask myself, how does 4 over x behave when x is huge? 4 over x shrinks down to 0. And therefore, the original function is going to behave like that as well, eventually. It's not 4 over x in the short term, but if x is big enough, it behaves exactly the same. And because 4 over x shrinks down to 0, the function will as well. No assumptions made at any stage. So that means if I were to graph it, let's maybe do that. I don't have a lot of time, but I'm doing it anyway. If I were to graph this, I have no idea what this graph looks like. It's a lot of work. But eventually, it's going to head down towards a y value of 0. I don't know which one it is. I can figure it out, but I don't have the tools right now. I do have a horizontal asymptote, though. Now I know I'm going over the time, but I need to very quickly just show you the last variation of how the numerator and denominator could interact, because I don't want you to think, oh, there's always a horizontal asymptote. No, not always. It'll take like a minute. Let's just do an example quickly. And I have like, let's just flip it around. X squared plus 4 over 3x. Long term. So let's take x going to infinity. It doesn't even matter which one. Y is going to behave like the ratio of leading terms. X squared over 3x. Which I then simplify to 1/3 x. So now I note that 1/3 x does what when x gets bigger? That third isn't going to slow the x down by much. If x is a huge number, a third times x is also going to get bigger and bigger and bigger. So we conclude that y is going to approach infinity as well. No horizontal asymptote, because infinity is not a number. And if I look at the graph very quickly, it says that as x gets bigger and bigger and bigger, the graph is going to go up. It's never going to stop. It's only a horizontal asymptote if it's approaching a specific y, finite y value, a horizontal line. If it just grows indefinitely, it's fine. It's the behavior of the function. There's nothing I can do about it, but we don't call that a horizontal asymptote.